Hi everyone, my name is Francisco McGowan. Thank you for joining us for this webinar on designing industrial structures in RISA-3D. Okay, so before we jump right in, if you have any questions, feel free to type those into the chat box on your end from your Zoom meeting. We do have our colleagues Ben Follett and Chris April who will be able to answer your questions. All right, so we're going to jump right into the types of models that we're going to be taking a look at today. So first off, we're going to be taking a look at a pipe rack model. And so just a quick description of pipe racks for maybe those who aren't necessarily from the industrial side of structural engineering. Sort of the classic definition of these is that they're essentially structures in petrochemical, chemical, and power plants that are designed to support pipes, power cables, instrument cable trays. They might also be used to support mechanical equipment like vessels and valve access platforms. And then we'll get more into this, but pipe racks are actually non-building structures that have similarities to structural steel buildings. And that's going to help us to sort of classify this structure in terms of finding the correct wind loads and seismic loads per the applicable codes. Okay, and so next we're going to be taking a look at an equipment support model as well. So something sort of along the lines of what you're seeing in these images here. So in this case, you're seeing a vent silencer support on the left-hand side. And then on the right, we might see, I think what might be a tank or maybe another vent silencer as well. But essentially the gist of what we're trying to get at is the lattice frame structure around these vents or tanks maybe on your project, and how you can use plates and of course members within RISA-3D to design these types of structures as well. Okay, so let's go ahead and talk about why we might want to have separate models for these two types of structures. So the first thing is going to be for pipe racks, as defined here in ASC 716, section 15521. These can be classified as supported at the base, and so they can receive seismic loading for chapter 12.8 and 12.9.1. And so we've already classified this now as pipe racks taking chapter 12 seismic loads. And so now what we want to do is maybe say, okay, let's confirm what type of seismic loads we need to apply to our equipment support or our vent silencer support in our case. And so if we looked at ASC 716, section 1531, for any type of appurtenance or model attached to another, because in our case, we're going to imagine that our equipment support is actually maybe sitting on top of our pipe rack or any large industrial structure. And so if the weight of that element is actually less than 25% of the total, as per this highlighted text here, then really you can use chapter 13 seismic loads. And so all in all, those are going to actually be two separate equations that have different variables. And we'll take a quick look at those if you're not familiar. So the chapter 12 loads are going to be the classic base shear equation, V equals C sub S W, where C sub S is your base shear coefficient and W is, of course, the seismic weight of your structure, giving you that V value, which is the base shear. However, per chapter 13, we have an equation that you're able to solve for F sub P. But there's some different inputs in here like RP, IP, Z over H, and such. And so this naturally gives you a different equation entirely. So this is kind of the first reason why you want to have two separate models for these two types of structures. Now, maybe you're not necessarily in a zone where seismic is going to govern the design of these elements or these structures. And so you need to consider wind, really. And so we can go to chapter 29 of ASC 716, which is going to pertain to specifically wind loads on building appurtenances and other structures. And so we can see here in the highlighted text, we see rooftop structures, rooftop equipment, open frames, and truss towers. So I'm personally going to go ahead and classify our structures into there, but definitely there might be another standard that you might feel that's more applicable to your types of structures. But this is what we're going to reference for our sake. Okay, but even when you go into chapter 29, we're still going to have a wind equation that's going to have this force coefficient CF that's actually going to vary for the pipe rack, as well as the silencer, the support for our vent silencer. So you can see here, I did my own little calculation based on these figures, 29.4-1 and 29.4-4, that give me the equations or the tables to calculate that force coefficient. And so I'm seeing here that it's quite a different coefficient. And so it might be another reason why you might just want to have these models be separate, because you're going to be applying a different pressure to each one. Okay, and then as we go through this webinar today, we're going to be taking a look at RISA-3D, RISA Connection, and RISA Foundation. And so all of our programs talk amongst one another. We just call that integration. So really what we're getting at is the fact that essentially loads and other model information can be transferred amongst our various programs. So in this webinar, these are the programs that we're going to focus on. Okay, so without further ado, let's go ahead and jump into our first model. So this is going to be our vent silencer support. Okay, so what we see here is our support frame, of course, and then we also see, if I turn off my nodes, we see some plate structures that are essentially replicating the vent silencer. And then I've also modeled a catwalk going around, and I purposely left one side off because I want to show you some of the new drawing tools available in RISA-3D version 18 that are going to make your life a lot easier when it comes to putting together models from scratch. Okay, so one of the first things I like to always touch on when coming into our new interface, if this is a new interface to you, is the fact that we have window docking. So to me, this is just a really handy feature in the sense that you can have multiple views open and display things on one window and display other things on another window. So I'm just going to go ahead and pop open another 3D view. Now, when I hover this over the center, you're going to see that I have the option to dock it in various locations. So if I want to do a vertical split screen, now I can display maybe on this window, I can go and on my quick view, I can say, let's display member labels on this side. But maybe on this one, I want to get a clearer picture of my loads. So what I can do is come to my display loads button here, and I can now, maybe if I turn off my nodes and go to a stick frame view, I can view these loads a little bit more clearly, and I can even kind of condense this information down even further, take away my nodes. And so now I can just have two different sets of information displayed on two separate screens. And not only that, so maybe you have a spreadsheet that you personally like to always have open. So maybe your member spreadsheet is that one for you. And so I'm just going to go ahead and close this 3D window. And if I want, I can say, all right, I always like to have this spreadsheet down below. Maybe it's just something I always like to have handy. And so you can do exactly that. And so you can continue working in 3D space and then also have your spreadsheet available to you as well. I personally like to have the full screen kind of available to me just to make everything as easy to see as possible. So we're going to go ahead and move forward that way. All right, so I do understand that some of you might be thinking that, why was the vent silencer in this case, or maybe a tank in your case, actually physically modeled? So really, it was just to showcase the fact that you can model plates using RISA-3D and actually use our generation tool, our templates, to create sort of complex geometries such as this one and really save you a lot of time. But not only that, it was really just to show maybe you're in a pinch and maybe you didn't get the reactions at the base of your structure from that tank or silencer in our case. And so you need to actually model it so that you can apply some wind to the face of it, or maybe you want to apply an acceleration to it so that you can get the seismic forces at the base and see how those transmit throughout the rest of your structure. So that's really why I modeled it in this case. But definitely we completely understand that a lot of times that those reactions are simply given to the structural engineer, and then they can go ahead and superimpose them on their structures and then continue the design of your structure. Okay, so if I show you, for example, some of the loads that I applied to this tank, we can see if I display my loads here and I display maybe my wind loads, you can see that I've got wind loads to the face of the plates, and I'll go into a little bit more depth on how to apply those and what they're doing behind the scenes. So before we do that, let's just go ahead and complete this structure. So I'm going to go ahead and turn some nodes on, and then what I want to show you is our new drawing tools. So if I come to our drawing tools and turn on lock to global axis, and I make an increment of 1.5 feet. I'll show you exactly what this does in just a second. So now I just click my members button, and I'm going to choose from my section sets that I created. This is going to make your life a little bit easier when you set up section sets. So I'm going to select the one that I called catwalk beam. And then what I want to do is just click a single point, and now you can see that I'm locked to the global axis. So that's what that button did that we just clicked. And not only that, when I drag over, you can see it automatically is going to snap to, there you go, 1.5 feet. And that's based on the increment that I set up here. So that makes your life a lot easier, so you can confirm exactly where you're going to extend that member out to. And then you can just simply right click to get out of that. But you're still in the command, so you can really go forward with drawing the rest of your model now. So we're just connecting the dots now. Maybe I want to just connect these corner points, but actually I want to get out of that lock to global axis command. So now I can go ahead and freehand and draw and connect the dots for the rest of this catwalk. Okay, so I can also use that tool for just the increment purposes. So maybe I want to add, if we see here these knee braces that I've added, I need to go ahead and add that for this side of the catwalk. So I can just go ahead and click this point, and if I drag down this length of this column here, I can see right there, that's where it says that's the increment point. That's 1.5 feet. So I can see that by the box where it says INCR as an increment. And so I can confirm again and rest assured that I'm clicking to the exact location that I want it to be modeled at. And so now that I have a point there, it's even easier because I can just click to that point to go ahead and finish that off. And then the last thing, we do have some infill framing. If I look down on a, let's see here, XZ view, you can see I've got these infill members here going around. So I just want to do the same thing on this side. So another way to showcase this is I can turn on, I've already got them on, but I have third points and quarter points available to me. So what I can do is as I drag my cursor, I can turn the increments off as well. As I drag my cursor along, we can see automatically it's going to snap to 1/3 point, and then I can just come across and you can see it confirms that that's the 1/3 point. So these snap features make your life really easy, so it really eliminates the fact that you used to have to sort of pre-plan or locate nodes beforehand so that you could then have a place to snap your cursor to. So this is going to make your life a lot easier and make putting together models a lot quicker. Okay, so now let's go ahead and just toggle through. We took a look at some of the loads, but if I turn my loads back on, we can sort of just hit our arrow key once we're in this drop-down menu and toggle through the various loads. We can see we've got some wind load and some seismic load and a little bit of dead load to maybe replicate some metal grating here going around our catwalk. Okay, and so if we dive again back into wind loads, I want to go into a little bit of detail about how we applied these and what they're doing. Okay, so the first thing we'll touch on is these open area wind loads. So what this is going to kind of connect back to the Chapter 29 ASCE 7 wind loads that we were taking a look at from our slides. So if you remember, we calculated a pressure essentially from that equation. And so once we've calculated that pressure, what we can do is utilize RISA-3D's smart capabilities to then apply this wind load as an open structure wind load. So I'll show you how to do that in just a second. So we can click area load. And then what I can do is I just simply pick a direction. In this case, it was in the X direction. And then for the load direction, I choose open structure. And I'll show you exactly what that's going to do for you. And then you simply type in a magnitude. And then I have these 4 points here. You can even click existing points on your structure and then just give it an area over which to apply that load. And of course, you want to choose a correct basic load case as well. So we'd want to put that into the WLX basic load case so that when we apply factors, it's going to get applied to the correct basic load case. So we've got, if I go back to my wind load in the X, that's kind of how we modeled this. It was really easy. And then we want to also cover the wind pressure on the side of this silencer as well. So if I take a look maybe in plan view, I think it'll be a little bit easier to see things. And if I zoom into these values, you can see here that it's about almost 40 PSF, but really I'm gonna explain this in just a second. So it's 39.9, and that's just because the face of this is not completely perpendicular to the wind direction. And you can see as I work my way around, the values actually get smaller and smaller, all the way to where the surface of the plate is nearly parallel to the direction of the force. So it goes down to 2.6, and then on this face, it's basically 0 PSF. So you can imagine that it would take a lot of hand calculations and just time to apply that load plate by plate. So what we've done is use the feature, a really handy feature called projections in RISA-3D to have the program calculate that tapered load as it goes around the sides of our tank or our silencer. So to do that, you can just go to plate surface loads. And then for the direction, this is the crucial part, is that you choose P as in projection, and then in the direction X in our case. So you can see here our global axes say X is this direction, so PX would make sense for us. And I can say this is going to go in the WLX basic load case. And then I can say for a magnitude, 40 PSF is what we did. And I can say apply to selected. So what I would have done beforehand is simply just select all those plates from my maybe top-down view. And I would have just selected all these by just clicking and dragging over them. And then I would have just applied this load to the face of them and simply hit apply to selected. And that's how I've gotten these loads. So you can see the features of RISA-3D make it a lot easier for you to apply more of these complex loads. And so if I solve the model here, we can go ahead and see what the result of this open structure load is. So let me go ahead and just solve that. So we'll solve a batch with an envelope solution. meaning you're going to get the results for each individual load combination as well as the envelope solution, which is just this real quick max and min. Usually the worst case scenario for your project is easily reported via that route. Okay, so now what we can do is go to our basic load cases, and you see that these are newly added. So these are called basic load case either 1, 2, 3, 4, 5, and it's the transient area loads for those. So if we see what basic load case 4 is, that's WL in the X direction, wind load in the X. So this one's called BLC4, transient area load. So let's see what those are called, or what those pertain to. So if I hit that, boom, you can see that all of these are really what they are line loads applied to the face of all of these elements based on the projected area that's facing the direction of that load. So all in all, if you had a really wide face that's in the direction of that wind load in the X, then it's going to get a much higher wind load because it has a larger surface area to take more pressure. But if it's a real slender element, then it's really going to take not too much. So if I render this, you can kind of get an idea to remind you of where we were. So obviously these wide flanges have a much larger surface area for the wind to contact, and then this angle is going to have a little bit smaller. So if I unrender this, we can see that this line load is kind of drawn proportionally. So this is a decently large, and you can see they get a little bit smaller as it goes to a smaller projected area for that wind. So that's going to make your life really easy, so the program will calculate those loads for you. And then as far as generating the tank, what I did was actually just use our templates, and I went to my cylinder. And so here you have a lot of customization options. So you can change, for example, if you want axis members or arc members, the plate material, so you can turn that on and off. And then in my case, I would have done a 360-degree sweep angle, so I could just type in 360 there. And then you can change the amount of increments going around by these sweep increments and also these axis increments, which are the vertical increments. So really at that point, you just go ahead and define a polar origin. Maybe it's just 0, 0, 0, hit OK. And that's how I ended up exactly with this cylinder that you're seeing here. So let's go ahead and turn off our loads for a second. Maybe turn off the nodes. And then as you can see, if I zoom in, we have a disk applied to the top and the bottom. So same thing, I just went to our templates. And in this case, I used circular disk for plates. And so really quick, I just typed in the radius, the increments in each direction, and the increments around the perimeter. And then the crucial part is that you just want to make sure that the increments around this quadrant match the increments around the cylinder that we just generated. And that's really important because of plate connectivity. So really, in RISA-3D, the forces amongst plates are only transferred at the shared nodes. So if the nodes don't line up perfectly, then you're going to find that you have a disk that's really just falling off the screen because it's not connected to the cylinder, or vice versa. So that's just a really crucial thing to keep in mind there. And you're not limited to having a disk top. Obviously, there's going to be some scenarios where maybe a tank has a dome top, and so we have one exactly for that. So you can come in here, and obviously maybe you don't want the stiffeners, so you can go ahead and turn those off, and then just create a plate element by defining a radius and a dome height and a few other options. And then lastly, maybe you're in a scenario where there's actually a conical shape at the top and the bottom, so that we have you covered on that as well. So you can come to cone, and then you can define all of the appropriate properties for that cone as well. And then you just go ahead and locate it with a polar origin, and then you can place this on the top and the bottom of your cylinder. Okay, so that's how to quickly generate plates for a structure like this one. And then also for the generation of the structure, although it is really easy with our new drawing tools to put something together from scratch, if your workflow consists of starting in maybe Tecla or in Revit, we do actually have a RISA Revit link and a RISA Tecla link, which allow you to transfer your models from both of those programs to 3D. And then you can send information back and forth as your design maybe changes. So obviously, if someone's already gone ahead and taken the time to put it together in one of those two programs, I would say why not take advantage of that and just go ahead and use the link and then create this skeleton structure. At least the plates will not transfer over, really, because plates are not handled the same way in Revit or in Tecla, but this entire support structure would be able to easily be transferred from Tecla into here or from Revit into here. Additionally, if it's part of your workflow to model these types of skeleton structures in AutoCAD or in any program that can create DXFs, we also have a DXF import feature. So if you come to File, Import DXF, you can simply locate your DXF and then import that to quickly create the structure that we're viewing here as well. Okay, so one other thing that comes to mind when I have a dense sort of element in my project, such as these plates that you see here, is being able to use selection states. So I'm going to show you here by orienting this in a vertical manner, and then maybe saying that I want to go ahead and use my select by property tool. And I'm going to say for members, I'm going to go ahead and select all the members on my project. So if I just check that box and I leave these blank, what it's going to do is select all the members on the project. So if I hit select, there you see they all turn blue. And so I'm going to close this, and what I can do is come to my selection states, my save selections. So I can click that, and I'm going to say save, and then I'm going to call this frame. So if I hit OK, I now have this selection saved for the future. So I can close that. And so now maybe I'm working, and then I decide, hey, I need to single out that frame. Well, that's perfect because I have it saved already. So I can just retrieve it, and then I can use one of our two lock tools to lock it out. So what I can hit my first lock tool is will completely get rid of anything else in the model from your view. It's still there, but it's just locked out from being able to see it. Or I can alternatively make that selection again. Oops, I need to hit retrieve in this case. And then I can hit my dim lock tool. So what that does is kind of in the name, it dims out everything else, but it leaves the elements that you selected in a selected state so you can still manipulate them as necessary. So this is probably more handy in a scenario where the selection you made took some time to actually select. So it was something outside of the realm of the select by property command where you couldn't necessarily have it. It wasn't smart enough to find the discrete locations of things you want selected. So if you've gone through the process for the first time of making those really specific selections of members on your project, then you want to go ahead and use that selection state so that next time you need to retrieve that same selection, you can quickly do so by coming in here and hitting retrieve. Okay, and so now what we can do is just go ahead and solve the model. So if I hit solve here, and we're skipping over a few things, but I'm actually going to go over all of them in our next model. This is just sort of a nice little intro into RISA-3D version 18's new interface and just some basics of the program. So right now, my favorite thing to do after solving a model is taking a look at the deflected shape. So I'm going to go ahead and turn off some of these nodes again, and I'm going to hit my deflected shape button here. And so you can see this is for dead load based on this drop-down menu here. So it's not doing too much. It's a pretty rigid structure. But if we start taking a look at lateral loads like ELX, you can see a little bit of lateral deflection there. But it is, again, it's a pretty rigid, framed out, braced out structure. So maybe I want to go ahead and kick up the magnification on that. So if I go to my View tab and I go to Results, I actually have a slider available to me that I can go and kick all the way up, hit Apply, and then you can see that that deflection is magnified by a lot more now. So I'm panning around just by holding Shift and holding the mouse wheel down on my keyboard, on my mouse. And then I can also use this cube and simply just click on it and then move this around as I need to dynamically. Or if I want to just spin about one axis, for example, the Y-axis, I can grab it until it turns blue and then just drag my cursor around and sort of check out the different deflected shapes on this. So I can do that for obviously the deflections in each direction for the different load categories. And really, this is just a nice way for the engineer to confirm that the model is behaving the way you would expect, really, which means that the results you're going to get are things you're going to trust. Because a lot of times, if you don't look at the deflected shape and you get some crazy results, it might just be because maybe you forgot to add a boundary condition or something of that nature. And so you have a model that is completely falling off the screen. And so that's why you're maybe getting some results that are unexpected. Okay, so let's go ahead and take a look at some more additional things, but let's go ahead and do it from our pipe rack model. So now what I can do is go ahead and just click and drag my pipe rack model into here, and I'll just say no to saving the changes. And so it's a really quick way of opening up another model. Perfect. So I can go ahead and just close out of that window. And then as you see here, we have something actually quite similar to the image we were looking at in our PowerPoint. So we can sort of pan around here. I can zoom in, and you can see we have essentially trusses that are spanning this long span from column to column. I've got some tube columns, and then I've also, since we don't really have a diaphragm element, I've added a lot of horizontal bracing to give us a sort of pseudo diaphragm element. And so we can pan around, and you can see I just widened it to about 2 bays as you come down the length of the structure here. Okay, so what we're going to take a look at now is the applied loads. So a lot of times, as the structural engineer on an industrial project, you're going to get a lot of loads from maybe a pipe stress engineer. And so I'll show you that I've applied some loads to sort of mimic that. So I can turn this into a wireframe view and maybe turn off the nodes so things are a little bit easier to see. And then I can go into my basic load cases and see, for example, some thermal loads that I added. So if I zoom in here, I've applied a 300-degree Fahrenheit thermal load. And so I just did that by coming to line loads. For direction, I choose T as in thermal. And then here you can just type in a start magnitude and end magnitude, and you can do partial length as well, specify a start and end location. Simply click to apply, click the member, and you've gone ahead and added that line load the way we're seeing it here. Additionally, I can view some pipe weight loads that I've accounted for. So these are just discrete point loads that I've added. And then also maybe pipe reactions from seismic loads. I've gone ahead and applied those as well. So maybe that's something, again, you get from your pipe stress engineer. And then sort of following along the same path we did for the previous model, I've applied some open area wind loads because we don't really have a diaphragm element to apply a wind load to. So we want to account for the wind acting on the face of all of these members that we've modeled. So if I come to, let's see here, WLX, maybe wind load X, here we go. We can see I've done the same procedure and I've just covered the entire face of it with this open area wind load. If I click on it, you can see here in the properties on the left-hand side that I've got the 30 PSF applied for wind load in the X, defined as an open structure wind load. Okay, so here's now how we're going to account for seismic loading on this project. So again, we don't really have a diaphragm, but we do have the seismic load generator tool on RISA-3D. So if I go ahead and click on this in our advanced tab, we're going to find a few inputs that we need to input from maybe our geotechnical report or just the values that we looked up ourselves. And here's where we're going to input those. But the limitation right now is that you need to have a rigid diaphragm for the program to then determine that point load that needs to be applied to that diaphragm so it distributes amongst the rest of your structure to get that load all the way down to the base. So what you can do for the time being is actually apply some rigid diaphragms. And what I'm going to do is just apply them only for a split second, and then I'm going to remove them because, again, we don't actually have those on our project. So if I come back to the Home tab, turn some nodes on, let's get some labels. And what I do is I just come into my diaphragms spreadsheet, and you can actually just click in here and add a new line. So if I say I want a diaphragm at the elevation where node 55 is, as you see there in the left-hand side, it's going to go ahead and add that. And I'll display these in just a second so you can actually see them. So I'm going to do 2 more because I have an elevation at N64 that I want it to have a diaphragm. Again, this is just going to be momentarily. We'll go ahead and go back and delete these. But essentially what I'm doing is going to have the program do the vertical force distribution of seismic forces for me. And then I'm going to go ahead and utilize that to apply those as point loads. So I have a diaphragm at node 61, node 64, and then 55. So if I go back to my quick view, I can go ahead and display those. So if I look at an elevation view, we can see that I have 3 planes of rigid diaphragms. Perfect. So this is what I need in order to use the seismic load generator, at least just temporarily. Okay, so what I can do now is go to the advanced, go to seismic, and then here I can say, okay, go ahead and calculate my loads for me. So it's doing exactly that. Here's all the inputs. Here's some additional details. And then ultimately, this is what we're looking for. So the seismic generation force results. So there's diaphragms 1, 2, and 3 at their respective elevations. And then you also get the force in each direction at each level. And then also the weight that it's considered. But ultimately, this is what I'm caring about, is the force in the Z direction and the force in the X direction at each level. So it's doing that vertical force distribution for us. And so what I'm going to do is go ahead and just make note of these values. So let's just make it a nice number in our heads and say 7,000 pounds, for example, to the diaphragm at this highest elevation. So I have 7,000 pounds going up there. Okay, so now as I promised, I'm going to go ahead and jump back and delete those diaphragms because, again, we don't truly have an infinite plane of rigidity. We don't really have a true diaphragm element modeled. So I'm going to go ahead and delete the selected rows. And then what I can do now is I still have that 7,000 value in my head. And so what I can do is go to IsomerXY View, and I can select all of those nodes at that uppermost level. And what I'm going to do is come to the properties, and if I hit this drop-down menu, I can see that there's 142 nodes up there. So now I have the 2 values that I actually need in order to solve this really simple division problem. And that is 7,000 pounds divided by 142 nodes. In that case, that's about 49 pounds. Or if you want it to round up, you can do 50 pounds. And so what you can do at this point is you can say, okay, I'm going to go ahead and apply some nodal loads as a load in the X direction with a basic load case of earthquake load X with a magnitude of 50 pounds. And then I can simply hit click to apply, and then I can box over all these joints and add that load. So I just added it to the load we already had, but just to kind of show you that really quick workflow in order to have the program sort of calculate the loads that you need to each diaphragm. So that's a quick crash course on how to do that. So I just went ahead and undid those so we could go back to our normal values. And I'm going to go back to an isometric view. And then we can go ahead and just turn those off to kind of give us a cleaner slate to work with now. Okay, so now we've sort of covered the wind and seismic, but definitely I have to imagine in industrial structures, you're going to get into moving loads potentially as well. So let's pretend maybe we have a monorail beam with a hoist and trolley system. So we can actually use moving loads in RISA-3D to actually model and analyze this. So what I can do sort of to create one from scratch is I can go to my moving load spreadsheet here. And so what I've done is I've selected a moving load pattern, which can be added simply by clicking this ellipsis button here. And we can go ahead and just edit the one I already have. So you have this nice little graphic of a truck and its various point loads that it's imposing. And then basically you're going to go ahead and just type in the magnitude here, the direction of the load, and then the distance between the two loads. So in my case, it's just a 5-foot distance between two 10,000-pound loads. So I can close out of that. And then all you have to do is simply type in the nodes that you want that moving load to move across. So I have mine already typed in here. But what I would do if I didn't have them is I would go back to a plan view. Actually, this is a good time to use our selection tool again. So what I can do is orient this in an elevation, and I'm going to select all of these, this entire plane. So if I go to ISO, you can see what I have selected. And then I'm actually going to hit the lock button, and this is another great time to use that tool. So if I go back to a plan view now, maybe in XZ, and I display my nodes, now I can see exactly the nodes that I need to follow or that I need to punch in order for my moving load to go and follow that path. So if I go to moving loads, you can see here I have N, let's go ahead and close that. I have N492 as my first node, N391, or actually I can go all the way to, I can go ahead and skip forward and type in the node, and then I can type in my last node here, which you see is N318, right there. Now you might say, okay, well I want to confirm what that moving load's doing. I see it in a spreadsheet format, but I actually want to see it move, and we have a feature that's going to cover you from that perspective. So if I just go to my view and hit moving loads, I can say, go ahead and display for me this moving load case called trolley. So if I animate this, you can see here we have our loads moving across that monorail, and we can track it and confirm that it's doing exactly what we want it to do. And we can see here it's going to approach that curve, and we're going to make sure that it's going to go around the curve and then finish off on this last linear piece. And then we're going to be happy with the moving load that we've applied. Perfect. So it's doing exactly what we wanted it to do. And now we can rest assured that our moving load is correctly accounted for. Okay, so now let's go ahead and we're going to go ahead and show you some different selection tools. So we've kind of naturally gone through this and working through these two models so far. So you can do things like use our box to select. You can also grab different selections of elements on your project by holding Control at the same time as clicking and dragging. So if you saw that, there's a plus sign by my cursor now, meaning it's going to go ahead and add to the selections you have. And so this is making it easy to go ahead and do different selections across my model. And if I want to unselect a group, I just hold Shift and click, and now you see a minus sign. So now if I box that, it's going to go ahead and unselect that information, and I can do that for this group of elements as well. Okay, and then we also have our legacy features for striking a line through elements. So if I click here, everything that was intersected by that line is now selected. And you have a quick unselect all, and you also have a quick select all tool as well. And then you can invert the selection by using our invert selection here. So maybe if I dragged and clicked and dragged to grab a few of those elements, and I want to invert the selection, I could use that tool to do exactly that. And so section sets was something I originally brought up just for a quick second, but let's go into a little bit more detail about what those do, because I personally am a huge fan of those. I think that they save you a lot of time when you're working through your models. And so we're going to go ahead and take a look at that. So if I jump into my section set spreadsheet here, we can see that I have a few already created. And simply you just go ahead and hit enter in here, and you can create a new line item to create a new section set. Let's go ahead and delete that row. And so what I've got here is a different section set for various elements that are really repetitive across my structure. So for example, I have one called chord. So if you can imagine, if I go to my model here, that's for all of these elements, all of these trusses have a top and a bottom chord. And then not only that, for the web elements, I've called them vert. you can imagine that there's probably maybe 100 of those vert elements. So what this does is allows me to group them all together. So if I decide that I want all of these web elements on these trusses to be an HSS 4x4, I can just simply come in here, either just type in the value, or I can search for my database of shapes and say HSS 4x4 and choose an appropriate 4x4 for my project. Once I do that, it updates all of those potentially 100 of elements in just a couple clicks, rather than having to click on each one and change it to a new shape. Also, it's going to play into a little bit when you do suggested designs. So that's the program's built-in capability to give you suggested shapes for your structure, whether they be over-designed or under-designed. So we'll take a look at that here in just a second. Additionally, actually, let me go ahead and jump back in there so we can cover the different databases of steel that we have. So if I jump into the section sets, we can go ahead and open that up. And then I can jump into, actually, let's go ahead and maybe go to our advanced, and then we can go to our shape database, is where I can show you some of those. So if I go to hot rolled, it's obviously not always the case where you're going to be doing an American project. So we have Australian shapes, British, Canadian, Chilean, Chinese, Euro shapes, Indian, Korean, Mexican, and so on and so forth. And so you can go ahead and just change that database, and you have all the correct shapes and properties associated with those as well. So definitely, if you have international projects, we have you covered on that front as well. Okay, so now we're going to go ahead and use some modify tools. So some of you may have noticed, but I have essentially like a special truss moment frame system for the longitudinal direction, but for the transverse direction, I don't really have a lateral system quite yet. So what I want to do is use a section set that I created called brace, and I'm going to go ahead and put some braces in. So if I go to my members and I say, let's use my section sets, and I want to use the one called V brace, as in vertical brace. So I can just go ahead and start clicking and drawing those. And now I could do this across the rest of my project here, but I was fortunate enough to have some equal spaced bays. So I know that these are actually 30 feet, but I can confirm by pressing F5 on my keyboard, clicking, and then clicking the next point, and you can see here it says a distance of 30 feet. So what I can do is just click to drag these two braces, and I can go to my modify, copy, global copy, and I can say in the Z direction, as you see Z there, I want to go negative 30 feet, because that would be in the negative Z direction. And if I hit apply to selected, I can do exactly that. So now you see the braces were copied over to the next bay. And if I know that the rest are 30-foot increments, I can say, okay, now I want to go negative 60, so on and so forth, negative 90, negative 120, and then lastly, negative 150. Okay, and so now I have one more bay on this side. So I can get clever with my modification tools again, and I can just make that selection, and then I can hold Control my keyboard, make that selection, and then make this selection. And now I know it's actually 15 feet going across this way. So if I look at my global axis in the X direction, I want to copy those over 15 feet. But again, that's in the negative X direction. So I want to globally copy in the negative X. So negative 15, apply to selected. Perfect. And so now I've completed the lateral system for my project really that quickly. Great. So now we're fully stable for our model for both directions. And so we can go ahead and take a look at how we could have used the templates for trusses on our project instead of modeling this sort of these trusses one by one as far as the elements within them. So that's personally what I did. I modeled this one truss here, and then I copied it multiple times using that copy command we were just using. However, if you wanted to, you can definitely come to our templates and you can use our truss tool to go ahead and generate that. So you can change the materials as you need to. You can change the different panels. Those are just the widths between each one of these vertical elements, essentially. You can change the distance between those. You can make a scissor truss if you need to by entering a value here, raising that center point of your truss as well. And then you choose basically the different section sets to create the top and bottom chord, the verticals, the diagonals. So really you can fully customize your truss here, hit OK, and then you can imagine you would simply have a truss generated for you. And then again, you can use those modify tools to go ahead and copy those across your project if they are in fact repetitive. Using the select by property again. So if I want to go to members and I'm saying, hey, I want to go ahead and just, for whatever reason, select all those V braces that I have modeled. I could go in there and click one by one and ultimately get them all selected. Or I can go to the member type and I can say, select for me all of the V braces and hit select. And so you can see all of those are selected accordingly. But as you can see, I actually forgot that I had selected the vertical members for the trusses as V-braces as well. So I just want to keep that in mind. You can actually get a little bit more specific with the selections as well. By choosing maybe the section set would have made more sense. Maybe I could have used the V-brace selection set. So if I go ahead and overwrite the previous selection and hit select, then I can do, that's ultimately the goal that I was looking to accomplish. Okay, and then we took a look at the dim lock already. And so another crucial thing is going to be your member design rules. So again, RISA-3D is a great analysis tool, but it's also a really great design tool. So here's where you'll come in your member design rules spreadsheet to define things like the max depth, the min depth, max width, min width. So this is going to be if you have maybe architectural constraints or just constraints working with other trades. For example, beam depth is obviously a really big one. So if you said you could only ever have a 20-inch deep beam, you can type in a max depth of 20 inches there. And then for the deflection, you can come into here. And then essentially what you would do is select a load combination to run your load combination, your deflection check on, and then you can choose a corresponding ratio for the program to check against that. In this case, we have L/240 set. I don't have any load combination set up for deflection, so I'm just going to go ahead and set that to none. But essentially what you could do is set one up for dead load, live load, and then dead load plus live load if you needed to. Or if you have any other deflection considerations on your project, you can go ahead and set up load combinations for those as well. Okay, so I'll go ahead and click out of that. And then we can also show you the load combination generator. So if I go to load combinations and I go ahead and hit the LC generator button, I've already got a lot of mine generated for myself. But just to show you how I got there, if I hit LC generator, I have the options for gravity, wind, and seismic. And then here I have various options for generating deflection load combinations, including roof live load, snow load, rain load. And so you basically just go down the list here and you can choose your different regions. You can see the various regions we have and the various codes we have for the region. And then you would choose your wind load and the X and the Z, generate seismic. You can choose for wind load, seismic load in the X and the Z. And then for overstrength, you can do the same thing if you need those on your project. So I can go ahead and hit close here. And then that's how I would have generated all of the ones you see in the background. All right, so let's go ahead and just solve the model again, batch with an envelope solution. Okay, and now we're seeing our multi-core processing happening right in front of us. So it's actually solving multiple load combinations in parallel instead of having to solve them one after another, which really saves time on really large models where there's a lot of load combinations. Okay, and so now again, we can take a look at those transient area loads to make sure the wind was applied correctly to the face of all of our elements on our project. So if I go to display loads and I say, show me the transient area loads for basic load case 4, for example, I can see that these columns, which were decently wide, 8-inch wide faces, are getting this 17.5 PLF to the face of them. And then I have this fairly deep bottom chord that's getting its wind load. And so you can really follow through to see how much wind load all of these different members are taking on their face. Okay, and then one of my favorite things to do after solving, aside from checking out the deflected shape, is going to be taking a look at the color-coded results. So if I hit this result icon here, I can see the numerical value, and then I can also turn on the color-coded option by hitting Unity check here. And so this is going to be just for load combination 7, but if I change this to display me the envelope results, I can see here that it's getting a lot more colorful. And so you can see I actually have a lot of failures. So all of these red elements are going to be, if you look at our legend, meaning that they're failing, meaning that there's a Unity check value that's greater than 1. So we do have some work that needs to be done on our project, but we also have some over-designed elements. So as you see here, these darker blues will reflect a 0 to 0.5 Unity check. So we have some things that are over-designed and some things that are under-designed. So again, we can really utilize the power of suggested designs in RISA-3D to give us that most optimal and economical solution for our projects. And then before we take a look at suggested designs, let's first take a look at the code checks from the spreadsheet here. So if I open up code checks, I can also view these results by going to code check, and then I can say, show me the worst case scenario on the project. So I can go ahead and sort these and say, show me the max to mins so that I can see the worst case. Perfect. So now you see these really bold red values here, making it pretty clear that these are failing right now for strength at least. And so what I can do now is say, I'm actually quite surprised that this M70 which if I wanted to go ahead and look up where it was, I can just go ahead and probably, let me clear out the results for what I have back there and just go ahead and reset those results. And then I'm going to turn this to a stick frame. And if I, again, go back to my code check spreadsheet, I'm going to say, well, where is M70? So what I can do is actually right click this and I can show, actually I can go back to my spreadsheets and I can say, select me that member. So if I go back here, I can see that that member is now highlighted in blue, so I can see exactly where it is. Not only that, but if I wanted to use my quick find tool, I'm going to go ahead and deselect that. I can go to quick find and say, take me to M70. So I just simply type M70 and I can also auto zoom to that view. Hit OK, and it's going to zoom you right in and then also have that member selected for you. So that's another easy way of finding members on your project. And then the last thing I'd want to cover here is, again, let's say you're quite curious as to why the value is so high. Maybe you weren't expecting that. So what you can do is jump into the detail report for this member by right-clicking on it and saying, take me to the detail report. And it's going to go ahead and launch that open for you. So a detail report, for those of you who aren't familiar, is going to be really what it is, what it says in the name. It's just basically every single detail about this particular member. We have these for wall panels as well. So all of these crazy material properties and shape properties and really in-depth design properties. The diagrams are very useful as well. So we have your classic shear moment and deflection diagrams. So we also have stress diagrams and additional axial and torsional forces and axial stresses. So you can always click on these to expand them and you can view different load combinations. And then you can also drag your cursor along and then view the values at discrete locations along the length of your member. Okay, and this is actually my favorite part of RISA-3D version 18, which is going to be our expanded code checks. So before, you might have been in a place where you basically, maybe you had to, you were basically putting faith into the program that the results it was giving you were 100% correct and there was nothing to be questioned. Or maybe you had to put in the legwork to confirm that the results were in fact matching your own hand calculations. But now we're actually completely showing to you all of the calculations that the program is doing under the hood, if you will. So if I go to axial tension analysis, for example, you can see here the equations, the description of the equations, and the variables. So we can take a look at the bending and axial, which is ultimately the governing case on ours. And so we see here we have a unity check value of 0.49, and we have our equation here. And so you can say, okay, well, where is MR, or where is MCZ? Because I'm quite curious about how that flexural capacity was calculated. So I can just go to flexural analysis for strong axis. And then here it'll expand for me that line by line calculation of the moment of the flexural capacity for this member in particular. So you can see even the CV calculation is done for you. So literally everything is laid out. Each variable, each equation, even the description of the variables and the equations are laid out for you. It's checking if it's non-compact or compact flanges. So really thorough calculations to settle your curiosities or just provide in your calc packs to appease any plan checkers that might be checking your calculations. Okay, so now what we can do is go ahead and take a look at suggested designs. So if I close out of this, I really need to check out my suggested designs because we saw we had a lot of failures. So if I go ahead and open up suggested designs, I can see here the current shape and the suggested shape. And so these are the different section sets. So for saying, for example, for my chord 5, but I actually need to kick it up to a W6 by 15, and then it tells you the controlling criteria here. In our case, it's all for strength. There's nothing deflection governed so far. So what I can do is simply hit resolve with suggested shapes, hit OK, and it's going to do exactly that. It's going to resolve it with those new suggested shapes plugged in and see if we reach the optimal solution. Of course, it's going to be a little bit iterative because there is going to be a force redistribution as you stiffen up certain members and make other members more flexible. So we can go ahead and see our suggested design. And it looks like we have none left. So that means we've actually reached the most optimal solution for our model. So that's a really great feature to really let you rest assured that you have the most economical design for your structure. And we can confirm by, again, coming to our code check spreadsheet and sorting these from max to min to confirm that everything is going to be in fact below 1.0. So we're at 0.98, so exactly right. So we're agreeing with those rules that we set up for ourselves. And then again, you can confirm this on a color-coded basis by using our unity checks on a color-coded basis and choosing envelope here. So you can see the highest sort of range we have is this magenta color, which is going to be everything from 0.9 to 1.0. And then everything over 1.0 is red, which is why we don't see any red here. So we're really happy with our design now. It's all finished up. And so now what we can do is take the member forces essentially into RISA connection for steel connection design. So integration is going to be coming soon with RISA-3D version 18. Right now it is available in RISA-3D version 17, but what I've done in this case is just sort of imagine that the connection design needed to make some progress, and so I essentially transferred those forces over to RISA connection, but I just detached the model. And so what you can do before we do that is if I click a connection or any member here, you can see that there's a RISA connection properties drop-down menu. And here's where I'll go ahead and select the various connections from our list. And then that's how the program will know when I use my director tool to send it to RISA connection that that's the connection assigned to that member, and it's going to go ahead and send all the forces over from that connection joint. So what I'll do is just jump right into RISA connection now. So I've got this file opened up, and you can see that I've got a various amount of connections in my project here. We can see that I have a lot of shear tabs or clip angles. If I scroll down here, I've also got some base plate connections as well. And then I also have some vertical brace connections as well. So let's go ahead and just jump into one of these base plate connections. So as you can see here, it's telling you the governing unity check and for the correct load combination. I've already detached the model, so the load combination isn't registered just yet, but we can go ahead and that's a feature that's available to you once you have the program integrated with RISA-3D. So at this point, you can really just pan around the model. This is a great way to do it in 3D. And you can also click on this, so it's also interactive. So you can click on this, and as you can see, it highlights the section for that particular element in the properties on the right-hand side, and that's where you can make changes. So maybe I wanted to change this connection type, and so maybe I want to change, I can change that by looking here at our connection type and going to maybe a knife around a knife plate, and so I can change that and pan around and see how that updated my connection. And additionally, the 2D views are also going to be really handy. So if I go and just let me undo this connection really quickly. So if we go to my 2D views, we can view more of a drafting style view. And here's a great way to make dimension changes. So if I click this 40-inch dimension, I can change that to 30. And then I can see how that my base plate got smaller. And then I can continue to make any dimensional changes I need to. So if I go to my reports, this is the great part about it, is it's going to be a nice little summary at the beginning telling you if you passed in the max unity check. And then the base plate is going to be the base plate specific limit states are going to be checked here for you. So you see all of these passes, the unity check values, the required capacity, and the available capacity. So not only that, but you can expand these as well and have a really nice format of the equation checked. You see here the equation from AISC 36010. You can confirm that here. And then you see all the variables that are plugged into that equation and even a description of those variables so that you can really easily get in there and see what you need to tweak in order to make your elements pass. And so you can do this for all the various interfaces. You can see going gusset to column, we have all of these different checks. And so you can imagine how long this would take without the use of a program like this to check all of the limit states that are technically required per code that need to be checked. So you can see how much work there is done for you here and how clearly it's laid out. So that's just a really quick crash course on RISA connection. We do have a really long list of connections available to you as well, simply by coming into our new connection window, and you see we have it broken down by shear, moment, and truss and brace, and we have a long list of connections here. And you can always feel free to submit us new connections for further development on RISA connection. Okay, so that's a quick look at doing that. And then also what I can do is open up the foundation version of our model here, where I've transferred all of the base reactions over to that model to design the foundations. So it's a similar story. We're going to get integration here pretty soon with RISA-3D version 18 and RISA Foundation. But again, let's just go ahead and imagine that our foundation needed to go ahead and the design on that needed to start moving forward so that we can get some preliminary pricing to our contractor. So what I can do is just go ahead and close out this model. And then what I'm going to do is just go ahead and open up RISA Foundation. So if I go ahead and just pop open that, we can jump into that pipe rack foundation model. And essentially this is what you would get. You would get the program just automatically opening up RISA Foundation for you. And then you can jump in. And I've already got some footings modeled, but what I want to show you is that it's essentially just transferring over the categories for all the different loads. So here are the dead loads for our model. And if I go to an isometric view, you can see and zoom in to confirm that those are loads that you feel comfortable with applying to your foundations. And you can do this for the various different load categories on your project. So if I come down to maybe the wind load in the X direction, for example, as I come down here, I see earthquake loads in the X, and I can really get a nice feel for the types of loads that my footings are going to see, so I can confirm that any designs I get are meeting what I would expect for my intuition. So if I go back to a plan view here and I render this, you can kind of get a better idea. I've got some pad footings and I've got some grade beams tying those together to help me resist any overturning or some uplift that might occur on any of these footings. And so at this point, I can just go ahead and hit my footing button here and say I want to apply this footing called footing 1. And all I have to do is just box over those nodes, and I'm going to have 3 footings applied. And then I want to go ahead and apply some grade beams. So if I hit draw or modify beams, I can go ahead and apply something. Let's say I want a depth of 36 inches and a width of 24. And I can define whether the ends are fixed or pinned. So I'm going to go ahead and do fixed end just based on the way that I'm personally going to maybe detail this in reality. So I go apply, and I can just turn off these snap points so that it snaps right to the node. Perfect. And so I can confirm again by going isometric view to make sure that I'm happy with the way that my foundation system looks. Okay, so before we press the design button, let's go ahead and take a look at what our footing definitions say that our program should abide by in order to give us a footing design that we're actually happy with documenting. So if I jump into that footing definition spreadsheet, we see here that you can define the material. You can force equal bar spacing. A group design is a way to take the worst case design of any one footing and apply that to the rest of the footings if you'd like to make your construction documentation really simple. You can force top bars. In the geometry, I always like to do force square so that I always have square footings. And then here's the upper and lower bounds that you're going to set for the program in order for it to give you the most optimal solution based on the designs that you like to present. So I personally like to do a min width and a max width of, a min length and a min width of 3 feet. And then I've capped it at 10 feet for the max length and max width. And then for the max thickness, you can set that here. Maybe I want to go up to 48 inches if my uplifts are really high. And the minimum thickness I'll keep at 18. You can also change the thickness increment, so the program only ever recommends to you thicknesses on a 3-inch increment. And then if you have a pedestal, you can go ahead and apply those here. You see we have right now a 24 by 24 by 2 foot tall pedestal assigned to these, and so that's just going to come into play when the program does the punching shear check on those footings. And so now we can say that I'm happy with the footing definitions, or essentially the upper and lower bounds for these footings. And so I'm going to go ahead and solve the model. So I can go to my load combinations, and I've actually already generated those. It's actually quite the same as the previous load case generator. I can just go ahead and hit that button and then choose my correct code. And then I want to generate load combinations for strength and ASD load combinations so that we can check our soil at ASD, and then we can check our concrete elements using strength design or LRFD design. Okay, and so now I've got all of these generated for myself, and I'm going to go ahead and just hit the equal sign to solve that entire model. So you can see really quick there. And so we can look on a plan view now, and these are actually to scale. So it looks like our loads are actually quite small, and we're getting footings that are actually quite small. So I can jump into the detail report for any one of these spread footings, for example, and take a closer look at the details of it. So you have right here at the top a really nice sketch giving you the geometry of the footing. And then you also have a nice little rebar layout, even in the pedestal. It's calling out the rebar, the different covers on your footing. And then here's some more in-depth information about your footing. And then we get into the actual limit state checks like soil bearing. So you see the max bearing here, the allowable bearing pressure, and then the ratio. And you also have it presented to you in a graphical format where the red is going to indicate the higher points of stress. And then here we get into more of the limit state checks that you would have to perform for a footing. So things like footing flexure for the top bars, footing shear check, pedestal design, concrete bearing, overturning, and sliding. So it's really covering the entire gamut of checks that you need to perform for a spread footing. And then if you ever need to do a quick, just to quickly see, where your project might stand, if you say, well, where would I be if I did a 4x4 footing? You can see it's a 5x5 right now, but if I hit redesign and type 4x4 and I hit OK, you can see I've got a 4x4 now, but I can scroll down and I can see immediately that there's a lot of red standing out. So my max bearing is actually exceeding my allowable. So I can say, okay, so maybe I just need to go back to the design that the program came up with, which was ultimately the optimal solution. So now we're happy with that design. And then we can do the same thing for our detail report for our grade beams. So we can click that and then take a look. That one actually didn't get one because it classified as a deep beam. So let's go ahead and click this one, for example. And then you can see here the various ACI 31814 code checks performed for you, as well as a breakdown of the rebar locations throughout the length of the beam. So it's truly optimizing for you the layout of the reinforcement throughout the length of the beam. But if you wanted to, you can of course extend this across the entire length for construction purposes, and you get a nice little cross-sectional detailing of that beam, so you can confirm that the program was analyzing your beam according to the way you're actually going to detail it. Okay, so that's a really quick crash course on RISA Foundation, and in general, walking through starting from RISA-3D, going to RISA Connection, and then even going to RISA Foundation, and you can see how all of them work together to really save you a lot of time without having to transfer any loads, and just have all that information stored within one software suite. So thank you so much for tuning into the webinar, and please do not hesitate to reach out to us at support if you have any technical questions, and also feel free to email us at info@risa.com for any sales related questions.